Okay. If you would go back to your notes just for a second for section 1 before we continue with section 2. I mentioned as you took the quiz just now that there's one thing that I have not spoken to you about yet regarding symmetry, and a topic comes up when you talk about symmetry that where you have to learn to identify an equation as either an even or an odd equation. Even, odd, and actually there is a third possibility. There's a possibility that the equation is neither one of those, okay? So this is how it works. For an equation to be even, it has to be symmetric to the y-axis. It's as basic as that. It's not a very complicated concept. An even function is symmetric to the y-axis. Whereas an odd function is symmetric to the origin. And you and I know, because we've done enough examples together, that there are problems which are neither one of these. They're not symmetric to the origin. They're not symmetric to the y-axis. Sometimes we have problems that aren't symmetric to anything. We've seen that, okay? But if you're not symmetric to the origin and you're not symmetric to the y-axis, then you're a neither situation. So on the test, okay, when we finally take the test on this chapter, that will be a question I will ask you. When you're doing the symmetry part of the test, I will include the question, is this function even, odd, or neither? You'll have the 3 choices, and you'll just circle the one. Now, how will you decide that? Well, you will do all your symmetry work first, and then you'll look at your answers, and you'll go to where it says origin, and you'll say, did I put a yes or a no here? If you put a yes by the origin, then it's odd function. If you put a yes by the y-axis line, then it's an even function. It's not extra work for you. It's just a matter of looking at your answers that you just got when you did all your symmetry work and seeing if there's a yes by the origin or a yes by the y-axis, or neither one of those have a yes, okay? Now, some of you may be sitting there saying, well, Ms. Russell, is it possible we'll get a problem where there's a yes by the origin and a yes by the y-axis? Could there be problems that have both of those symmetries? Here's the answer to that question. Yes, there could be equations that have yes for the origin symmetry and yes for the y-axis symmetry. But those equations are not functions. They're not functions. And what we're talking about right now, and maybe you better go ahead and write it, is even function versus odd function. Now, your question maybe is, well, how am I supposed to know if it's a function or not? Just by looking at the equation you give me and looking at my answers to the symmetry questions. Well, You may not be able to do that in reality, okay? The deal is this. I know which problems are functions or not, okay? And I won't even ask you, is it even or odd, if it's not a function, okay? I will not even ask the question, is this an even or an odd function, or neither, when I know we don't even have a function with what we're working with. So you don't have to worry about that, okay? If you see that, if the directions say, that if you see the words even, odd, and neither, to circle the one that is right, then you can be sure you have a function and you'll be able to circle either even, odd, or neither. Am I clear about that? Do you understand how I'm saying it? The burden's not for you to worry about that. That's my problem. Okay? All right.
Is it possible for an equation to be symmetric to all of them, like the y-axis and y equals
Mm-hmm. It is possible. I can offhand think of one shape that you all are familiar with somewhat that would have all those symmetries if it's in the right spot. Can you think of the shape that would have symmetry to all 5 of those checkpoints that we do? The origin, x-axis, y-axis, y equals x, y equals negative x.
Square.
A square is possible. Giving an equation of a square, however, is something that would require actually 4 different equations, one for each line, and so that's not something I would use in a problem. What about another shape?
A circle?
What about a circle? And specifically, where would that circle have to be located?
On the origin.
It's got to be where the center is at the origin. So look at this example. What do you think about that shape? Is it symmetric to the origin?
Yeah.
When you spin it, obviously, when you spin it, it still looks like a circle all the time, right? If you fold it on the x-axis, does the top part land on the bottom? When you fold it on the y-axis, does the left side fall on the right side? When you fold it on this line right here, do the 2 sides come together? When you fold it on this line, you see what I'm saying? So, yes, a circle is a shape that could have all yeses, if its center was the origin.
So that wouldn't be a function though, a circle.
A circle is not a function though. Why not?
Because it's symmetric to y-axis and origin.
Okay, but before you even knew about that, why is a circle not a function from old knowledge that you had back in Algebra 2 and Advanced Math?
It's not a line.
Well, lines aren't the only functions. Parabolas can be functions, certain parabolas. How did you test a graph in the past to see if it was a function or not?
The vertical line test.
The vertical line test. Does a circle pass a vertical line test? If you do this, how many times does the vertical line touch a circle? 2 times. And which means what? It's not a function. Okay? All right. But again, that's really not your problem. Okay? That's going to be my problem to know in advance whether the problem I'm giving you is a function or not. And I'll have to, be alert to that. All right. Let's go back to our families of functions then. Okay? Now, remember yesterday I